All right, hello everyone. You should be watching this on Friday, March 20th. I figured you guys would all be missing chemistry and my corny jokes and my voice, so I figured I would post this video to YouTube where I go through the PowerPoint talking about our new material. So as you can see, I just have the aim, activities, and homework. There's no do now because, well, you guys can't do it now, but we're going to be talking about pH, which all of you guys knew about before we took this little hiatus. But we're going to actually define what pH is and how it relates to acids, bases. And then you'll see I'll just post a little worksheet that goes along with pH, which you'll submit just to make sure you really understand what's going on. I'm going to post like a little Castle Learning review just since it's been over a week since we talked about this stuff, but I'm going to only do it on the lessons that were before our break and the stuff from today. So it'll only be on the basics of acids, bases, the two theories, Arrhenius and Bronsted-Lowry, and then pH and pOH. And that will be due Tuesday. I'll just make it due at 8 a.m. Doesn't really matter. But make sure to do that just so we don't forget what these things are. So we have pH and pOH. You guys know that acidic things have a pH from 7 and 0, that range right there, and basic are above 7. But what in reality does pH mean? pH is a measure of the H plus concentration. So how much hydrogen ions, or remember we could use the word protons, are in a sample. So something that has a low pH, which is very acidic. Let's take in our little example here, a vinegar, which has a pH of 3, right? That's telling you how much H plus is in your sample. Things with a lower pH, such as hydrochloric acid, way on the left, with a pH of 0, has more H plus or more protons. So acids have more H3O, which again is just another way of saying H plus, than OH. And the lower the pH, the stronger the acid. Do not get confused with that. The lower the pH, meaning if we have a pH of 1 compared to 7, the stronger the acid, the more H3O plus, or the more H plus, or the more protons. So if we have a pH of 1 versus a pH of 6, we can compare them. Let's say that at a pH of 1, you have 0.1 molar. Remember that big M is molarity, which is moles per liter. We can rewrite that, and remember that's scientific notation, 10 to the negative first. That relates to a pH of 1. So if 0.1 molar relates to a pH of 1, some of you guys would think, oh, 0.06 relates to a pH of 6. Not quite. If you notice, what did we change from we went from a pH of 1 to a pH of 6? Well, now we have all these zeros in the beginning. And if you count up, we actually have 1, 2, 3, 4, 5 zeros. So when we went from a pH of 1 to a pH of 6, it was really like moving that decimal point 5 times. So in this case, we can write our H plus concentration as 10 to the negative 6, which, ding, 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 should be setting off a little thing in your head, because that is directly how we get the pH of 6. When you rewrite your concentration with a base 10, and I'll explain what that means later. So whereas an acid has more H3O plus than OH minus, a base is just different, right? A base has less H3O plus than OH, or more OH minus than H3O plus. And again, the higher the pH, the more, let me make this blue, the more OH plus minus you have, sorry. So if we had a range of, let's say, 10 and 14, 14 would have more OH minus, right? Because it's a stronger base. There's more OH minus, there's less H3O plus. So when we talk about H3O plus and OH minus and pH, all we're talking about is the amount of each thing in the solution. So drain cleaner all the way at 14 has a lot more OH than H3O plus. Hydrochloric acid has a lot more H3O plus, H plus, or protons than OH minus. So the pH of a solution, this is going to get a little mathematical, but stick with me, is really equal to the negative log of H plus. And the concentration of H plus is usually given in scientific notation. So for instance, we have 1 times 10 to the negative second. If we put that into negative log, which is just log is base 10. You guys don't have to know it that much, but it shoots us back this number too. I really went through this fast because there's a little trick. To simplify a calculation, you just take the exponent on the 10. So in this case, right, your H plus concentration was equal to 10 to the negative second. So if we just take, oh, that was awful. 1 second. 10 to the negative second. That's a little better. So if we take that negative 2, well, we can't have a negative pH, but we can just say that the pH is equal to 2. So this is the little trick. You don't need to worry about all of this stuff at the top with negative log of H plus. In reality, you just take the exponent and make it positive. So what is the pH of these solutions? If we have 1 times 10 to the negative 11, well, we're just going to take that exponent, which in this case is negative 11. That tells us the pH. So our pH here is equal to 11. And if we are at 11, which is above 7, that tells us that we are basic and that there's more OH negative. Simple. Just take the exponent. That's your pH. If you're above 7, you're basic. You have more OH negative or hydroxide. If you're below 7, you're more acidic and have more protons or H plus or H3O plus. What about here? 1 times 10 to the negative 5. Well, again, all we're going to do is take that exponent and make it our pH. pH is equal to 5. We're under 7, so we are acidic. And we have more H plus. And finally, 1 times 10 to the negative third. We're just going to take that exponent. Our pH is 3. We are more acidic, and we have more H plus. What if I were to look at sample B and sample C? Between these two samples right here, which one would have more H plus? If we were showing a video in class, it would say, pause the video now and think. But in reality, this one right here is going to have more H plus because we are a lower pH. We are more acidic. More, come on, more acidic. So again, the lower the pH, the more acidic, higher the pH, the more basic. And that brings us to this little diagram. This is your pH scale. So I can throw the numbers up at the top. So if we have a pH of 0, it shows you in red right here what your H plus concentration is, and it shows you in blue what your OH minus concentration is. So you can see if we have a pH of 0, our OH minus concentration is super duper small. So it's 10 to the negative 14th, very tiny. We have no OH negative. Whereas on the other side, if we have a pH of 14, we have a lot of OH negative and not a lot of H plus. So in other words, I could do this. I could draw a big H plus all the way on the left of our pH scale, which gets smaller and smaller as we go to the right? Because there's less H plus. Likewise, we can draw a big OH minus all the way on the right that gets smaller and smaller as we get more acidic. This is just a nice visual representation of what's going on, right? These OH and H pluses are getting bigger and smaller in concentration. So we would call this acidic, this neutral, and this basic. And pH, as we said, is the concentration of hydrogen. You can think of it as the power of hydrogen, pH, right? How much hydrogen you have. We're going to introduce another term called pOH. Well, if pH is power of hydrogen, pOH is like the power of OH. It's the number of OH ions you have. And what's special is that pH and pOH equal 14. So our max that we could be on our pH scale, if you notice, is 14. That's because of this. That's because your pH plus your pOH is equal to 14. So if we had a solution and we added an acid, how is that going to change the amount of H plus and the amount of OH negative? Well, like we said on this scale on the left-hand side, we're adding an acid, we're adding H plus, and the amount of OH is going to go down. If we add a base, it's the opposite. The amount of H plus is going to go down, amount of OH negative is going to go up. So when we change pH, we're really just changing the amount of hydrogen by a power of 10, and I'll explain what that means. This relates directly back to, to the exponent. So let's say, I don't even need that. Let's say we changed pH from 8 to a pH of 7. Well, the pH is going down. We're getting more acidic, which means our H plus concentration goes up. Think back to this, right? We're moving from 8 to 7. We're getting more H plus. How much more H plus? Well, the concentrations would be this. H plus for a pH of 8 would be 10 to the negative 8. For a pH of 7 would be 10 to the negative 7th. So it increased by 1, you can think of it as like a factor of 10, so it's 10 times more concentrated. What about here? We're changing from a pH of 6 to a pH of 4, again getting more acidic since we're lowering that pH. How much more acidic? Well, it's a factor of 2 now because we're changing. You can think of it like this. From 6 to 5 is 10 times, and then from 5 to 4 is 10 times. Well, what's 10 times 10? 100 times more concentrated. And then lastly, we're going to do pH of 2 to a pH of 5. So if our pH is going up, we're getting more basic. Oh, this should say, this should say pH increases, H plus decreases, right? Because we're getting more basic. How much more basic? Well, we're changing from 10 to the negative 2nd to 10 to the negative 5th. So again, think of it like this. We have a pH of 2 going to 3, going to 4, going to 5, and each one of those decreases in H plus concentration is 10 times. So 10 times, 10 times, 10 times, which means it's 1,000 times, and this should say less concentrated. I'll fix this for when I post the PowerPoint. But it increases by 3 factors of 10, so it's 1,000 times less concentrated. So by every time, every pH like factor you're changing it by a factor of 10, either 10 times more acidic or more concentrated, or 10 times less concentrated based on the direction you go in. So let's see here. We have a solution with a pH of 2, has a hydronium ion concentration 10 times greater than a solution with a pH of blank. Well, if we are 10 times greater, that's 1 factor, right? 1 factor of 10. Which means we're either going to go down to 1, a pH of 1, or up to a pH of 3. But how do we know which way we're going? It's this word right here, the greater word. If we have 10 times greater, it means we are lower in pH. So we're right here at a pH of 2. We're going to have 10 times greater H plus than a pH of 3. So a pH of 2 has 10 times the amount of hydronium ions than a pH of 3. If we were looking at, let's say, 9 and 11, right? If we change from 11 to 9, what's happening to the H plus concentration? Well, from 11 to 10 would be 10 times, and from 10 to 9 would be 10 times. So in total, we're changing by 100 times. Are we getting more or less acidic? Well, our pH is going down, so we're getting more acidic, which means we have 100 times more H plus. right? So why is pH important? I'm just going to do a little blurb about why we care about pH. Well, think back to the living environment. All right, proteins function better in certain pHs. So if you see here, the protein in your saliva likes a pH around 7, neutral, but pepsin likes a pH of around 2. So different proteins like different pHs. Also, between 1700s, don't ask me how they got data from 1700s, but from 1700 to 2018, the ocean pH has decreased from 8.25 to 8.14, which in reality means it's getting more acidic. And you may think, oh, it's only a difference of 0.11. That relates to a 30% increase in acidity. And why is it bad that our oceans are getting more acidic? It has to do with shells. So all the shells you find at the beach are made of something called carbonate. So there's carbonate in shells. And what happens is when carbon dioxide, which is in the atmosphere, dissolves in water, it makes carbonic acid, which breaks down the carbonate in shells. And guess what? CO2. You guys know where CO2 is coming from. Fossil fuels, right? So fossil fuels and greenhouse gases like CO2 are affecting the oceans and making them more acidic. So this is a little visual of what's happening to our ocean. So you have coral that's healthy December 2014. Over time, it's dying because those carbonate ions are reacting to make calcium carbonate. It's not good. You do not want that. And then this is a projection of what shells will react to. It'll be the ocean water in 2100. So this 45 days is based on 45 days in 2100 or 2100. So they're saying that a normal shell will disintegrate in only 45 days if our oceans continue to get acidic year after year after year. So what I recommend you guys doing is going through this PowerPoint with my little voiceover. Make sure you understand this, right? The fact that pH tells us how much H plus and OH minus are actually in your sample or your solution, and then give that worksheet a shot. Again, my office hours are going to be 9:30 to 11 and 12 to 1:30. So you can email me, you can text me on Remind if you're having trouble with any of this. Okay? Stay safe, stay healthy, and I will see you guys as soon as possible.